Can you see my screen?
Yes, sir.
All right. So last time what we tried here to describe, or what we described, is how the Taylor terms in the Taylor expansion approximates the terms of the Taylor polynomial approximates the function. Okay. So let us look at this one in a graphing representation today. Okay. Before going further uh, into this proof of this theorem, let us look at few graph. Can you see the graph?
Yes, sir.
All right. So let's look at function e to the power x. Simple function. I mean, very simple to understand, but of course, not a simple function as we'll see later on. There is a definition of simple function. That is a different thing. All right. So now let's look at the first degree polynomial, that first degree Taylor polynomial. So 1 plus x, right? And see how it approximates. So if you look at this one, this is approximate. The first one is constant. This is y equal to 1. So this line will be the first one. All right. Now let's add more term. So 1 plus x plus x square uh, by 2, right? Is it true? See the graph. See, it is getting more close than this line, right? Can you see it? Or shall I just make it full screen? And maybe let's do that. Can you see it?
Yes, sir.
All right. So let's add more term. 1 plus x. What will be the next term?
X cubed by 6.
Right, x cubed by 6. Square divided by 2. 2 plus cube divided by 6. Right? So let's see how it works. See the orange one? See this portion. It is closer than this red one as well as this one. Right? So even if you see on the top, see this orange one goes nearer to this the original curve in green than this red one, right? So let's add one more term. What will be the next term?
X to the power 4 by 24.
X to the 4 by 24. See the purple one? Yeah. Now is it a bit clearer? Now what we are saying that it will be as you increase the degree, the 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 function will the polynomial will get closer and closer to the function. So here around that it looks like that everybody is in the same line, but it's not actually if you go microscopic. This tangent line touches at the point only, not anywhere else. So similar thing, this will also touches there. This will also touches only at one point. This all will touch at one point only. It is not same in a neighborhood or something. Okay. Any question here? Or anybody wants to take any other function? Yeah.
Sir,
Yes.
so not from here. I had a question from last class. Can I ask it now?
Yeah. Sure.
Last class you said that there may be other polynomials which approximate this function, but these
Right.
are the polynomials that are constructed with the best ease. But
Right.
what do we really mean by approximation when we say there may be other polynomials which approximate it? Because approximation was defined to be that particular polynomial which matches at all the derivatives, right?
No, approximation does not mean the matches at the derivative. Approximation means that function is close as well as the derivatives are also close. This
Yes.
is
So,
the polynomial which matches with the derivative. Other polynomial may not match.
but if any polynomial doesn't match at the derivative, how can the derivative be close? I mean, at the point it has to match to make the derivative close.
No, 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 no. Why should it match at this? Okay, so you are saying this. Well, if you look at one, see, derivative, first derivative is 1. If you look at 1 minus epsilon, does that matter? Instead of coefficient 1, if you fix 1 minus epsilon, 1 minus 1 over n, let's say, for
But
large n.
1 minus 1 over n for large n, that would be a worse approximation, right? That won't be a better approximation than what we got.
I mean, what do you mean? How do you compare the approximation?
Maybe by how close they are.
Right, so what do you mean by how close they are?
When we are subtracting 1 by n, we are putting in it a difference, right?
A difference of what?
A difference of 1 by n, we are putting in it a constant difference of 1 by n.
That's okay. What is the problem there?
Then it becomes a worse approximation than what we got, because in what we got, we in the Taylor polynomials there is
Mhm.
constant difference associated. So this is always a better approximation, isn't it?
No, but I mean, I am not clear how you are saying this better and worse, right? You have to compare, and your
The
comparison is
difference
not.
of the functions, the difference of the
If you take difference of the function, it will be less than epsilon for given any epsilon.
mm,
So that will be possible to make. Okay.
but suppose
So,
we choose a deleted interval, I mean a delta interval, and
mm,
the Taylor polynomial, the
right.
difference in that delta interval of modulus fx minus px for these Taylor polynomials will be the supremum of the difference between a difference of modulus fx minus px
Mm.
for the Taylor polynomials will be less than the supremum of difference of fx minus px for the non-Taylor polynomials, because
No,
there's always
that's not true.
1 by n associated with it.
No, so that's not true actually. So you see, what do you mean by close? Difference between fx minus px. So given epsilon, there exists a delta in a neighborhood. You are doing the approximation. For given epsilon, there exists a delta such that fx minus px, the modulus, is less than epsilon, right?
Hmm.
Less than epsilon
Hmm.
on that whole interval for all x in that interval, right? That is the approximation. So
But
in there, in that sense, if you take 1 plus x or 1 minus if the coefficient as 1 minus 1 over n for large n, that will give the same approximation. Because as n tends to infinity, it is going to 1 plus x only, right? So if a sequence converges and another sequence converges to, let's say, for each n fn, for each n you get this fn gn j which converges to fj as j tends to infinity, or fn as j tends to infinity, then you will get a subsequence from this gnj, right, that converges to original function. So this is perfectly fine if you look at, I mean change the coefficient a little bit. The main problem here, so Taylor polynomial is uniquely determined because this the coefficient becomes actually the written in terms of the derivative of f. Okay. Now here you see, if I add here something plus x to the power, let's say 10, and see what happens. It will get close. It will get close. So it is this one, right? So it will get close, of course. But the point is, see here, of course, the coefficients depends on the coefficients. But if you look at a small neighborhood, it is getting close. If I remove this one, let's see what happened. Yeah, see. So the point is, higher order derivative, if you add near the small neighborhood, that will get close. But Taylor polynomials is uniquely determined in terms of the derivative, and this gives a approximation. Right, the best approximation part, that part, I'm not saying anything here. Right here, the best approximation part, that actually one need to compare to get best something, what is best and what is worse or worst. So that part is not clear now. One, we do not have a measure to, something to measure how something is best approximate, something is not. So that actually part of some, numerical experiments, which with some data one can approximate, one can get a curve which approximates best, and in certain sense. So that is not there here. Here, what is there is something approximates. So this polynomials, no other polynomial approximates. That's not true.
okay, sir. Okay, sir. Got
Okay.
it. Hmm.
And not only just here we need the derivatives, right? But actually, uh, for any continuous functions, there exist polynomials which approximate. Okay. Of course, not then the derivatives will not be close, but the function will be, there will be polynomial which will be close to the function, continuous function, on a closed interval, uh, for every epsilon. Epsilon closed. So you see, even if derivative does not exist, polynomial can approximate. But here, since derivative exists, so in terms of the derivatives, you get a sequence of polynomial or a polynomial which is close by. All right. Any other question?
Sir, one more thing I don't understand. Sir, you mentioned that if we take p of x naught equals f of x naught, then we have a polynomial which approximates it. Uh, like we have a
Say that,
polynomial
Say
which
that again.
if we take p of x naught equals f of x naught, then we have a unique polynomial which approximates f. Like there can't be any other polynomial which has p of x naught equals f of x naught, right? And the derivatives are also equal.
And the derivatives of the equal derivatives of this form, right? So what did I say? It is, let me go back. Yeah, so this part is a little bit tricky. So, right, so you get the polynomial px is determined by this way. Yeah, right. So this was the point. So this polynomial of this form is uniquely determined.
If we said Pn x naught equals Fn x naught, like where n being the nth order derivative.
Right. So yeah. So now if you write this f to be px plus something, right? Px is of this form plus some rn or rnx, rn plus 1x. So this one is uniquely determined. This part is uniquely determined because this part gives you, this is not just arbitrary. It gives you in terms of the derivative of the function. Okay, so polynomial has to be of this form. If it is not, then it is not uniquely determined.
Right, sir. So what I don't understand is if you have a polynomial which approximates it in the sense we defined earlier, I'm
Hmm.
not able to understand how. So given that both f and p being a polynomial is smooth, and even say f is a smooth function, I'm not able to see how it could be possible that both a polynomial approximates f in this sense, and also the functional value of f and p need not be equal at the point x naught. I mean, it looks like it would follow from the fact that the polynomial approximates the function that the functional value of f and p are also equal at the point, which would mean that the polynomial has to be unique.
No, no, no. If they approximate, then why should the value of the polynomial? Value of the polynomial has to be same as value of the function. So
So,
what do you mean by approximation?
so because we can make the neighborhood arbitrarily small, and we know that it's continuous, which means that we can't have any point discontinuities or anything like that. So
You are saying, see, you are saying so how do you want to approximate? Here it is closed. So 1 by n, does 1 by n approximate 0, the sequence? So you get 1 over n something n, 1 over n, right, near to 0. But is it 0?
no, no.
Right? But 1 over n, look at the function fx equal to 0, and a function close to 0 is 1 over n, right?
Yeah, right.
Right? But it is never 0.
Yeah, okay, okay.
So that is how, and there will be many sequences which converges to 0, right? Not just 1 over n. So that's how this, in this case also that is true. Given a function, you get a sequence of polynomial. Yeah, by Taylor series, you actually get a sequence of polynomial if it is infinitely differentiable, which approximates around that point. All right. So as you increase the degree, it will get closer and closer to the function. Now, it does not mean that there exists no other polynomials which is closer to the function. Just like 1 by n converges to 0, approximate 0 doesn't mean that there is no other sequence which converges to 0.
Okay, sir, got it.
Right? Yeah. Any other question? No, this Taylor series part is little bit tricky than the other things, and it actually gives a lot of stuff about the function.
Sir, don't we say that the quadratic polynomial, the cubic polynomial will be a better approximation than the quadratic polynomial?
Right, right. That's what
So how do
I
we
showed,
compare
right?
them? How do we compare them?
Because you get the third derivative is also closer to the third derivative corresponding function.
But how
Right?
does that? Why does that ensure that it would be a better approximation?
Because you are not just putting there is each step. So suppose you are looking at continuous function and you want to approximate continuous function. What do you mean? You will take uniform approximation. So uniform convergence you will take, right? The supremum you will take in a closed interval. That is what you should do. If you go first differentiable, consider all functions which are once differentiable. Okay. Now if you approximate that set, then you will take supreme of the function as well as supreme of the first derivative. All right. So not just functional value is close, it is the derivative is also close to the derivative of the function. All right. Now if you go to the second, twice differentiable functions, right? Then you can actually approximate till the second derivative, till the second derivative. And if you go to the third derivative, which actually once if it has second derivative, twice differentiable function, then you can have by the last theorem which I last stated last time, that you get a quadratic polynomial plus some remainder term, right? If the differentiability is up to third order, yeah, up to third order, then you get a quadratic polynomial. If the function is differentiable up to fourth order, then you get actually a cubic polynomial plus some remainder term. So,
Uh,
right?
so when I got that point, but when we say better approximation in this case, what we basically mean is more derivatives match.
Right. More derivatives get closer. Not just
Okay,
matches, it
more
gets
derivatives get
closer
closer.
in a small neighborhood.
Yes, sir. Okay, sir.
Yeah, that is the sense. So you will see that this functions, continuous functions is denoted by ck, right? C interval, C of the something, some open interval, and first order differentiable it will be called C1. So maybe I should write this part since we have already made few comments. So here a notation. What happened? Yeah, notation. Yeah, so consider this interval AB. The AB is this we know it's collection of all continuous functions on AB, open interval AB. Similarly, this notation C1 AB is collection of all continuous uh, all functions if such that f prime is continuous on AB. C2 AB, collection of all functions if such that f prime, f double prime continuous are continuous on AB. C infinity similarly, collection of functions which for which every derivative is continuous. All right. So, this one, if you look at this class here in this case, we'll take you can take this supremum on compact sets. So is the what should I say, is the kind of metric. I mean, one can get the metric taking supremum on every compact set inside AB. So, I mean, this will be complete in that sense. Here in AB, you just not just take supremum on compact set, but you take supremum on the derivative of supremum of the derivative on compact sets also. Here you go the supremum of f, supremum of f prime, and the supremum of f double prime on compact sets of AB. And here on every compact set, and you will take on every derivatives, right? So that is how the I said this better approximation, in the sense that the derivative, that many order of the derivative can be approximated. All right, and you see here somehow the higher order derivative plays a role to get closer, right? So when you add just x, it comes from this line, this line parallel to x-axis to this tangent line. When you add again x square by 2, it even gets more closer. After we add x cubed by 6, it gets even more closer, this orange line. So some of the derivatives are playing a role to get into closer to that function. And yeah, and then here one would then one would real analytic functions which has power series, convergent power series, at every point of AB. All right, so these are class of functions you will be studying if you go further. It's not just, and then the sets will get changed. In this case, since you are in real line, you are looking at open interval, or you can take closed interval up to the boundary if you take the derivative. And later on, you can look at disks in R2, balls in R4, R3, so on. So these classes are actually well studied. I mean, are studied for every different domains. All right. So does this clear your doubts? Or if you have any question? Okay. So anyway, let's start. Let's go back to here. Right. So let's look at the proof of Taylor's theorem. So sometimes this power series, also called Taylor series. So let me see the theorem what we want to prove. So we have a function from closed interval AB to R continuous, and all the derivatives are also, all the derivatives up to the order n are also continuous. So at the boundary point, we are looking at one-sided continuity, one-sided limit of the derivative continuity, all these things. and n plus 1 derivative exists on open interval. We do not need n plus 1 derivative on the boundary for the proof of this theorem. Then fx can be represented as px plus rn plus 1x, where px is defined above, which means what was px? Yeah, px is this one. So yeah, we need the expression of px. Right, and Rn plus 1 x has the following form, which is this x minus x naught power n plus 1 by n plus 1 factorial fn plus 1 c. For some c in the line joining x and x naught, or I mean this is same, this form and this form are same. We'll see it. That oh well, this form and this form not exactly same, but one can get it from right here. So Rn plus 1 x is x minus x naught to the power n plus 1 by factorial n 1 minus theta all to the power n fn plus 1 x plus x naught plus theta times x minus x naught. So this point also lies in the line joining x naught and x. So theta belongs in 0 to 1. All right. So let me recall Px is f of x naught. So x naught is in, of course, in AB. X naught is in AB, and Px is fx naught plus f prime x naught into x minus x naught plus f double prime x naught by 2 x minus x naught square plus f3 x naught by factorial 3 x minus x naught whole cube and so on. And the kth term is fk. So I have taken up to n, right? So n plus 1, right? Okay, so we can take kth term fk x naught by factorial k x minus x naught power k plus the last term is fn x naught by factorial n to x minus x naught power n. Alright, so this is px, and we want to find actually rn plus 1x. Alright, so in the graph, if you see, we want to find actually the part of the function here which is difference between this green line minus the purple, or minus something. Okay, so in this case, so if in case of order 3, the difference will be the green line minus the orange one, and in case of order 4, it would be green line minus purple line. For each point, you look at the subtract between green line minus this. That would be the remainder. Okay, so this is what we want to find. And interestingly, this form of this remainder is this. So that is now the question. So why should the form of this Rn plus 1 be like this? All right. So So where to here what we'll assume, so represent Rn plus 1 x as x minus, so choose p, a natural number, any p, and we represent this, or maybe let's call this m instead of p. That will look good. X minus x naught power m, some function h. Okay, uh, we just divide Rn plus 1, Rn x, whatever the difference. So what we do here, what is this? This is nothing but uh, we define h to be fx minus px by x minus x naught for m. All right, so this is it. So this for x not equal to x naught. Okay, so this is what our definition is. We want to define a function h such that this is true. This is perfectly defined for x not equal to x naught, and for x equal to x naught we do not know. We'll see that. So we look at, you just multiply with this part. We look at fx minus px is x minus x naught power m times h. Is this clear? Now define a function phi on where? On, and this is defined on x belongs to AB, right? There's no problem in that. In fact, I mean, one can take closed interval as well. The definition makes sense, this one. Px makes sense, fx makes sense, and x minus x naught, one of division makes sense as long as x not equal to x naught. So define this phi from what? From uh, AB to R by P of T to be summation. Now here, so here what we do, we will fix x in AB. If I fix x and define phi t, which is maybe I'll write this not just summation form but the expanded form, ft plus x minus t times f prime t plus x minus t square by 2 f double prime t plus x minus t whole cube by factorial 3 f triple prime t and so on, plus x minus t power n by factorial n fnt plus x minus t power m h. All right, this makes sense. Yeah, one can define this to be just ht also. Yeah. Now note, this function has, of course, it is differentiable. Uh, right? It is f I is continuous on AB. Is this correct? See, ht may not be defined, but if you multiply x minus x naught times h, that is continuous on AB. And you can define x naught to be just fx naught minus px naught there. Right? So you get continuity of this whole term. So phi is continuous on AB. Now is phi is differentiable? Is it true?
Yes.
Hmm. So what we want is m to be strictly less than equal to n. Okay, we don't want more than that. So that will give you the differentiability of of phi, right? So it would be differentiable. Now x was fixed. X was fixed. So what is phi of x? Phi of x equal to fx, right? Yeah. See, other part it vanishes. If you put t equal to x, right? Phi of x equal to fx. And what is phi of x naught? If you put x naught here, f of x naught plus x minus x naught f prime x naught plus x minus x naught square by 2 f double prime x naught plus x minus x naught or 3 factorial 3 f 3 x naught plus x minus x naught to the power n by factorial n fn x naught plus x minus x naught power n hx, right? And this is nothing but Rn plus 1x, right?
So you wrote h of x here, but above you
Oh,
wrote
h
h
of
of
x,
x.
right. So there is a need to change here. So instead of ht, that part we need to make hx. Yes. We need this phi x naught to be just fx also, right? This is also fx. So this is px and fx is px plus Rn plus 1x, right? That gives you fx, and here see, this part gives you fx. So consider phi on x naught to x if x naught is less than x, and on x to x naught if x naught is bigger than x. All right. So we first fixed in the very beginning x naught, and here also we fixed x, right? And see the conclusion here. So we want this x naught here, and fx will be of this form, where Rn plus 1 is this, where C belongs to some x naught and x, right? So once you get this representation, this one, which is automatic, Rn plus 1 is just p fnx fx minus px. Once we get this one, we fix x. And x naught is already fixed. And then we define this function. Now this function is continuous on a whole of AB. In particular, it is continuous on here also. So phi is continuous on x naught to x. So assume x naught is less than x. Assume x naught is less than x. And so phi is continuous on x. Phi is differentiable on x naught x, and phi of x equal to phi of x naught. Which theorem to use?
Raleigh's theorem.
Right. Yeah, Rolle's theorem. Apply Rolle's theorem. There exists C in x naught comma x such that p prime C is 0. Yeah, this is important to have hx here instead of ht. Otherwise, you will have the derivative of h which we do not want. So let's take the derivative of phi. So phi prime C is f prime C plus here you have product rule, which means here minus f prime t minus f prime c plus x minus t x minus c is equal to c. We are putting f double prime c, right? Then there will be, let's look at next term here, 2 times, right? Sorry, here 2 times x minus t, and there will be minus sign for minus t. So this should be minus x minus t times f double prime t minus x minus c times f double prime c, right? And so on. Plus, let us look at the last part here. So this should be, well, there is the previous term also we need to look at, which is x minus t to the power n minus 1. So x minus c to the power n minus 1 f n. So we are taking derivative at this level. Fn c by factorial n minus 1 minus we take the derivative of this one. So we take the last part of the derivative of the previous term, and we look at the derivative of this last term. So here n times x minus t to the power n minus 1. So which means here n times x minus tx, which is x minus c n minus 1, and there will be minus sign because of this minus t. There will be factorial n here, fn c plus x minus c power n by factorial n fn plus 1 c. And then there will be here this term h does not depend on t, so it would be here only. So this will be m times minus m times x minus t to the power m minus 1 minus m times x minus c power m minus 1 h x. Right? Now this is equal to 0. Now there is some cancellation. See, here goes away, this goes away. Similarly, this goes away. Only part will be remaining here, this one. So this will be m times x minus c power m minus 1 hx will be x minus c n by factorial n f n plus 1 c. All right. Right. So now you take. So what we take is we fix m, right? M was arbitrarily chosen. M was what? M was a natural number. M is less or equal to n. Did I make any mistake? No. Right, this is true. Right. Now here you put yeah, this is fine. This is fine. Absolutely fine. So put p equal to 1. Put p equal to 1. So you can take, sorry, put p is not pm equal to 1. M equal to 1. Then from star we get cm equal to 1, this goes to 0. So hx will be x minus c power n by factorial n fn plus 1 c. So which is the remainder, sorry, remainder in the Lagrange form. Put m equal to n right? The last one. Oh, sorry. What did I say? Do you get this one? Hx is this form, but we'll have some x minus this power m, right? This x minus x naught will be there. Right, so this is also fine. And this, yeah, true. So we get, what we get is this one. So anyway, check the computation. If it is not correct, we'll do again. And if m is equal to n, then this should be n times x minus c m minus 1 hx. Oh, sorry, m is n, so this is n minus 1. X minus c power n by factorial n if n plus 1 c. So is this correct, this one?
Sir, can you explain how this corresponds to the remainder form? Because in that, first of all, we have x minus x naught power n plus 1. And here we have x minus c, the remainder form.
Ah, yeah, right. So this is x minus c, right? Yeah, true, true, true. So yeah, yeah. So PT is this one. PT is this one. This is fine. We want to look at this one, right? F of x, which is px plus Rn plus 1 x, right? So we need to look at here t as x equal to x naught, right? And we need to find h here. Yeah, that is true. We need to find, so x minus x naught power m will be there. The problem is here we are getting c, right? Yeah, you're right. This is a good point. So this is fine. So put m equal to 1. We might not get Lagrange's form here. So let me do this part again. So put first m equal to n. We'll get Lagrange's form here. So then from star what we'll get? M equal to n. So we get.
Shouldn't it be n plus 1 to get the Lagrange's form? Because then we will get in denominator n plus 1 factorial.
Oh yes. So yeah, so basically we need here. That is true. That is true. So here we need up to n plus 1 because yeah, this Rn plus 1, n plus 1 derivative. The amount it has, f has derivative till the order, we can go till then. So f has n plus 1 derivative. Yeah, that is true. So we need f n to be n plus 1. Right, you are right. So we get n plus 1 x minus c. Now you see that get cancelled. Yeah, I got confused in this. In n plus 1 hx x minus c to the power n fn plus 1 c by factorial n. Now this gives you hx to be x minus c gets cancelled. So this gets cancelled. This gets cancelled. And what you get is fn plus 1 c by factorial n plus 1. Right? So which is the not which is the Lagrange's form. So it is Rn plus 1 which is the remainder. Rn plus 1x which is x minus x naught power n plus 1 hx. Right? M equal to n plus 1. So this is x minus x naught power n plus 1 by factorial n plus 1 f n plus 1 c, which is the remainder in Lagrange's form. All right. Now, if you look at m equal to 1, m equal to 1, then we see what happens. So this should be here, right, this star. So m equal to 1, this goes away, m is also goes away. So hx is this x minus c power n, x minus c power n by factorial n fn plus 1 c. So first one is clear from here, right? So let's look at, right? So this one we got already. Now we need to get this one, right? Here, so right, so maybe we need to do some computation here. We have m equal to 1, which is x minus x naught times hx, right? So Rn plus 1 x minus x naught times hx, which is x minus x naught times x minus c power n by factorial n fn plus 1 c, right? But this is not the one, right? This is not the one. What is the problem? Right, so we need to put this one. So you will put c to be x naught plus theta times x minus x naught. Let's do that. You put theta equal to c to be x minus x naught plus theta times x minus x naught. Right, so that's what it is in the beginning. X naught plus theta times x minus x naught. for theta for some theta belongs to 0, 1, because if this is line joining x naught here, x here, any point C can be written as convex combination of this x naught and x, which is this one. All right, so now put this on, so we get Rn plus 1x to be x minus x naught, and here x minus x naught plus theta times x minus x naught whole power n f. So this is a picture, so this is different, whole power n f n plus 1 x naught plus theta times x minus x naught. There is a minus sign here, so this is x minus c, so this would be minus minus. So you see x minus x naught, and here x minus x naught gets common, so x minus x naught, there will be factorial n outside, to the power n 1 minus theta power n by factorial n f n plus 1 x naught plus theta x minus x naught, which is x minus x naught power n plus 1 1 minus theta power n by factorial n f n plus 1 x naught plus theta times x minus x naught. Right. So which is the remainder in Cauchy's form. Right, any question here? I'm sorry for the delay, but I think those who have problems already left. But when you are proving a theorem, it might take some time, and online is a difficult one to prove a theorem. So any question here? So you see, we get both the thing, the remainder in Lagrange's form as well as the remainder in Cauchy's form. All right, so we'll compute. Yeah, any question?
So one
Yes.
question.
Yes.
When you were talking about the differentiability of phi,
Yeah.
How did we argue? We argued essentially. Okay, so they are all polynomial forms. So they're all
True.
and we only need to check the differentiability of the last term, because the rest of them are all just okay. We need n plus 1
differentiability.
because fn. Okay,
Right, differentiability of Fn.
got it.
Right. So if since I was putting ht here, that would have been problem. If m is bigger than, you could not put. I would not have. I would not have access to put m to be n plus 1 if I take t here. Okay. That is the reason I wrote m to be less or equal to n, to make sure this, if you put ht here and here till, if you go up to n, even then it would be differentiable. But if you go n plus 1, then you cannot put ht here. There will be problem in differentiability. So the problem, when somebody pointed out that there will be x here, not t, that actually solved the problem, because we need to check this f prime, f double prime, f up to fn differentiable, and all this the coefficients are polynomial. There is no problem, right?
Why would it not be differentiable if the power, if it was h of t, because h of t is differentiable?
hx is this point.
hx is differentiable with respect to x even if m is greater than n.
No,
Because
at
f
x
of x is
near
differentiable.
x naught you have problems, right? See, near x naught is there is a problem. So this part, if m is bigger than if m is m plus one, then there is a problem here, right? Until this part m is n, this part would get cancelled in some way. So you have to check rather. So if m is n plus one, then h part is may not be differentiable here. Rn, if m is n plus one here, you put this whatever remaining may not be differentiable.
Okay, but that's not necessary because our phi does not depend on.
Right,
So,
right. So since yeah, that is true. That I mean, this putting x here solves the problem. Otherwise, you would have in trouble. We would have been in trouble. Yeah. Any other question? So next time, what I will discuss is some Taylor series of some functions as well as how the second derivative captures the geometry of the curve, or how the second derivative, what kind of information we can encode from second derivative for the function. Like the first derivative we saw, we have seen that it is first derivative greater than 0 implies it increases, less than 0 in an interval it decreases. So what kind of information one captures, one gets from the information of second derivative? Okay, so that would be the next discussion. All right, so I went 15 minutes further. I won't go more than that. All right, see you later.